let me explain what will help you to keep in mind as we go through lipids. This chapter, dealing with lipids, is a little less, or a little bit more diverse. Let's put it that way. A little more diverse than chapter 16 on carbohydrates and chapter 18 on protein. In what way? Well, in chapter 16, you saw how similar all the saccharides had a lot of things in common. They had a carbonyl and a hydroxyl group. They were 3, 4, 5, 6 carbons long, and they had OH groups in carbonyl, and they were soluble in water, and they formed polysaccharides. So they're kind of a unified group there. Yeah, glucose is different from fructose, but there's a lot of similarities between glucose and fructose. Chapter 18, amino acids. I started out that chapter saying here is the general structure of an amino acid, and the only thing that differs is the R group. So those are pretty unified bodies of compounds there. Lipids. The thing that lipids have in common is that they are not soluble in water. That's about it. Okay? Well, we'll make it simpler than that. But here, this is a pretty decent slide. If we talked about all of lipids, which are not soluble in water, there are simple saponifiable lipids, triglycerides, complex saponifiable lipids, phosphoglycerides. These are the two main things we're going to talk about. And then in non-saponifiable, we got steroids. So if you were to try to say what are the three most important groups in this chapter, it's this, and this. Those are the three most important groups. Triglycerides, phosphoglycerides, and steroids. There's other stuff in here. So so right over here I'm going to just put triglycerides. So you can kind of keep track of it. Phosphoglycerides. And you can see they're referring to these as simple and these as complex. All right, simple, there's only two components here. Two components are glycerol. This is a molecule you need to have a 3x5 cardon and memorize the structure of, and 3 fatty acids. I had you each make 2 carbons. We're going to put together 2 fatty acids, stearic and oleic. So they're only called simple, and you're going to say they look pretty complicated. They're only called simple relative to this, which is glycerol is the backbone. Did I spell that right? You can see glyceride in both of these names. They're both getting that glyceride name from glycerol. There are 2 fatty acids. There's a lot of similarity between triglycerides and phosphoglycerides. And then there is a phosphate group. With something on it. All right? So this is a phosphate group. So hence phosphoglyceride. Triglyceride, why? There's 3 fatty acids. There's no phospho group on this. Just 3 fatty acids. All right, so I'll just keep that up there as kind of a scoreboard. You can kind of keep track of these things a little bit. And we'll probably go through this at a little bit faster clip than I normally do. Let's go back 2 slides. Lipids. Lipids are biological molecules that are insoluble in water, but soluble in nonpolar solvents. These are typically nonpolar molecules. In general, they are nonpolar. So waxy, greasy, or oily compounds found in plants and animals are lipids. If you think of fat-soluble vitamins, you've heard of fat-soluble vitamins. They're falling into this class of lipids. They're not soluble in water. And matter of fact, what you'll hear in nutritionists and people dealing with supplements, you actually absorb fat-soluble vitamins when you have a little bit of fat in your diet. You don't have fat in your diet, you have a hard time absorbing fat-soluble vitamins. Did I go 2 slides? All right, they're an energy source. Lipids pack about 9 calories per of kilocalories of energy per gram, where carbohydrates pack about 4 or 5. So lipids pack a little more energy. Triglycerides provide energy storage in adipocyte cells. Phosphoglycerides, sphingolipids, steroids are structural components of cell membranes. Steroid hormones, critical to intercellular messengers. The sex hormones, steroids, lipid-soluble vitamins like A, E, D, and K, and dietary fat acts as a carrier for lipid-soluble vitamins. Provides shock absorption and insulation. Whales swimming around in cold water, big, huge layer of fat in the whale. They don't hardly notice the cold. All right, there's that slide. This is a kind of a good slide to come back and kind of where to hang your hat. Where are we? We're going to be wandering down through here and go one more step. We're going to look at what are fatty acids, because that's what triglycerides, that's one of the components. All right? This is one of the components of triglycerides. Your body can make fatty acids. It can synthesize them. It can take fatty acids and metabolize them and harvest the energy from them. So this is the path we're going to be on right now. We'll just mention that in one slide. What is a wax? They're saponifiable. Exactly what we learned in esters, where you can react an ester with sodium hydroxide. That's saponification. You can take these triglycerides and saponify them. All right, so let's look at fatty acids. And to do that, I'll tell you what, here's what I want you to do. In this row, just pass these back and just clip them together. Clip them together. You guys do that too. Crystal, take your little molecule, hand it back behind you, clip it together. We're going to need, in one case, we're going to need 7 of those carbons. So 2, 4, you're going to get 8 there. I'm going to need, okay, I'll get this right here. I'm going to Let's see, who's got one real long chain? Yours all done? I didn't get one. You didn't get one? What do you got here? 2, 4, 6, 8. 8. I'm going to make stearic acid here. 8 and 4, that should be, is that 12? 2, 4, 6, 8, 10, 12. 12. Let me just have all these. 12. How many carbons in stearic acid? 18. So we got 12 and 4 would be 16. 16. 17. We're going to need more of these.
I'll make them.
No. Hang on a second. Thanks, Danielle. Let's see. I think that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Stearic acid. There's stearic acid. It's a carboxylic acid. This is a fatty acid. It's a saturated fatty acid. Saturated. All single bonds. 18 carbons long. 21 students times 2 would have been 42 of these. I don't know. A bunch of you didn't make one. Oh, wait, what do we got here? We've got 2, 4, 6, 7. Hang on here. That's 9. Oh, you're doing all right. So we need 1, 2, 3, 4, 5, 6, 7. And we're going to put a double bond in there. And then we're going to go 1, 2, 3, 4, 5, 6, 7. I owe you an apology. We made plenty of these. 7. 7 and 7 is 14, 15, 16. 17. Okay, Danielle, give me a couple bonds. Bring me one tray up here. And we'll be all set. Okay, you hang on to that. Okay, Danielle's got the saturated fatty acid right there. Oleic acid, how many bonds in there? How many carbons? 18. They both have 18 carbons. One, 2, 3, 4, 5, 6, 7, 8, double bond. So 9, 10, 11, 12, 13, 14, 15, 16, 17. And they are long chain carboxylic acids. Carboxyl group here, this is nonpolar. Okay? That's the thing to keep in mind. Oleic acid has one double bond in it, and it is cis. So if this model wasn't so heavy, what you would see is this molecule is like an elbow right here. It's got a bend in it. It's kinked because it is a cis bond. If this were a trans, the double bond would come in one side of the the chain would come in one side of the double bond, it would go out the other side of the double bond, and it would actually lose its kink. No longer be kinked. It would kind of look almost like that one. This is a trans fat. It doesn't exist in nature. It's a result of processing foods, predominantly. Trans fats. All right? And these are they're not natural. They're unnatural. They don't occur in nature. What occurs in nature are cis. You with me? And that little kink right there, you're going to see at the end of the chapter, these molecules have a part to play in the cell membranes around every cell. So there is our unsaturated fatty acid, oleic, and there is our saturated fatty acid, stearic. Long, nonpolar part of it, the carboxylic acid is polar. It is water, it's hydrophilic. The rest of the chain is hydrophobic. All right, so these fatty acids, we're getting familiar now with the fatty acids that will make up triglycerides. These aren't the only two. There's a dozen or more fatty acids. Typically, they are 10 to 20 carbons long. These two are 18 carbons long. Usually you have an even number of carbons. So you'll find an 8, a 10, a 12, a 14, a 16, an 18, a 20. You'll find those, even numbers. They can be saturated like stearic acid or unsaturated like oleic acid. Only carboxyl groups and double bonds are present. The double bonds are always cis. The melting point increases with increasing carbon number. And then I want you to understand something interesting here. The melting point of this versus this are very different. They've got about the same molecular weight. This is a solid at room temperature. This is a liquid at room temperature. So by the time you reach room temperature, this is already melted because of that double bond. They're about the same molecular weight. They differ by just 2 hydrogens right here. Or right here. We would have one more hydrogen on each one of those carbons with the double bond. Over here we got those 2 hydrogens. It's not a whole lot difference in molecular weight, but there is a big difference in melting point. It's exactly why lard from beef fat is a solid. It's lard. It's white. You know, it's like Crisco. Why that is a solid and olive oil is a liquid. Olive oil. We talk about olive oil and you pour it out of the bottle. All right, so let's look at these. Let's look at these melting points. So here's stearic acid, oleic acid. These are 2 back in chapter 14. I said, learn the structures of these 2. You know, you could draw this one as CH3, CH216, COOH, whereas this one is CH3, CH27. Just keep in mind that that double bond is right in the middle of that chain. It's not just anywhere. It's right in the middle. So just like your elbow. Your elbow isn't just anywhere. It's right in the middle of your arm. So then you have a double bond here. And then you have another 7 carbons and a carboxyl group. That's oleic acid. Saturated have no double bonds. Unsaturated have at least 1, and it's always cis. All right, here's showing, there would be your oleic acid with the cis double bond and a bend in the molecule. And here's what I was trying to show you. If you came down through here, you're coming down through, zigzagging down through the carbon chain, and you zigzag right on through the double bond. This is trans. This is trans. This is cis. And cis is the naturally occurring configuration of these fatty acids. All right, the molecules they have this dual nature to them. At one end, you got a carboxyl group that is water-loving, hydrophilic. And the whole rest of the molecule is hydrophobic. And so that's what this tail is referring to. This is the nonpolar portion of the fatty acid, and this is the carboxyl end of it. And so it will form a micelle like that in water where, imagine that you got all of these. These are pointing out towards the water, and this is pointing inside into this sphere of fat-soluble tails. And so these things here can emulsify oils. Oils will dissolve in here. They don't like it out here. So they'll find their way into the middle of this micelle. And that's how soap works. All right, let's look at melting points. All right, don't pay attention to this for right now. Pay attention to this line. What do we got here? Here's the temperature at which this fatty acid melts as a function of the number of carbons. So if we had the one that was just 4 carbons long, 4 carbons long, 1, 2, 3, 4. So one that's long, very short. It would melt around. It would melt below 0 degrees centigrade. It would be a liquid. 6 carbons long, 8 carbons long. We're going up into here. 10 carbons long. Here's room temperature. So once you would get up to 10 carbons long, since the melting point is above room temperature, it would still be a solid room temperature. You have to get above, you have to get up to this temperature for it to melt. So all of these are solids. 10, 12, 14, 16, 18. So at 18 we're talking about stearic acid. 18. Melting point. 70, above 70 degrees centigrade. That's hot. You got to get this pretty hot to melt it. 70. I mean, a cup of coffee is 85 or 90. Go ask Starbucks. They'll tell you exactly what temperature it is. And if it goes above that, then something's wrong. Fix the machine. It's too hot. Someone's going to burn themselves. All right? Okay. So you follow that. Now look at here. 18 carbons. You put one double bond in it. Bam. Melting point drops by about 50 degrees. It's a liquid. That's a dramatic drop in melting point by adding a double bond. Add another double bond, linoleic acid, 18 carbons long, but it has 2 of those double bonds in it. And you drop it down again to about 0 degrees centigrade. 3 double bonds, and you're down to about minus 10 degrees centigrade. It's still liquid. Pretty neat, huh? Now here is the kind of stuff that's in omega-3 fatty acids. They're polyunsaturated fatty acids. Polyunsaturated, more than 1 double bond. Usually 3 double bonds. Where do we get omega-3 fatty acids from?
Fish oil.
Fish oil. Now if you were a fish and you had triglycerides in your bloodstream, would you like the triglycerides to be rock solid, hard, at minus 10 degrees centigrade? Okay, and these fish, salmon, they come in off the Pacific Ocean, they run up the rivers in Washington, they swim right past the old iceberg that's floating down from North Pole. The water's minus 5 degrees centigrade because it's salt water, it hasn't frozen yet. What do they have floating around in their bloodstream? They got triglycerides that are polyunsaturated fatty acids in them. So they're still liquid, minus 5 degrees centigrade. I've always been amazed at how smart those salmon are. Just amazed that they figured this out. Yes, we'd like to have those polyunsaturated fatty acids, please. So they won't freeze. That's it. That's where we get them from. And they're essential to us. We have to eat them. We have to eat fish oil or flax. Flax are swinging around in minus 20 degrees temperature sometimes, and they need oils in them that don't solidify. So there's the story behind the importance of double bonds in fatty acids, and that they do come in these different varieties. Here's just a table. We won't go into it too much. Here's oleic, cis-9 octadecanoic, stearic, just octadecanoic. Yeah, all right. Palmitic, you can just see palmitic. Palmitic is 14, 15, 16 carbons long. There's myristic, it's 14 carbons long, and there. Oh, I should have brought in my little bottle of, what are they? MCTs. Anybody take MCTs? Medium chain triglycerides? Okay, MCTs. This is liquid coconut oil. Anyone take that? Or put that in their food or on their breakfast or anything?
Maybe lotions.
Lotions, yeah, MCTs.
In your hair.
In your hair. I'll tell you one way they use these MCTs. They have a person, sometimes an infant, could be an adult as well, who really can't take on nutrient, can't swallow or digest for some reason. They got an intestinal problem. They will give them MCTs intravenously because these MCTs are easily absorbed by the cells and easily metabolized for energy. So if you have an individual who can't eat and they're lacking energy, they're actually dwindling, you can supply energy by intravenous MCTs. Medium chain triglycerides. Medium chain means these smaller fatty acids are going to be on these triglycerides. Okay, we got to build a triglyceride now. Some of these slides overlap with one another. You've already seen they're usually even, 10 to 20 carbons. That's kind of redundant. Structures of fats and oils. So the triglyceride is an ester. Triglycerides are triesters. Triesters. Okay, they're made up of glycerol plus 3 fatty acids. And here's what one looks like. Okay, let's take a look over here. There's your glycerol. 3 carbons with an OH on each carbon. Very similar to glyceraldehyde. Glyceraldehyde is 3 carbons, but it has an aldehyde on it. This, you take the aldehyde off and put an alcohol there. You got an alcohol on each of the carbons. Glyceraldehyde has an OH on 2 of the carbons and an aldehyde on 1. This is glycerol. It's a triol. It's this portion of the triglyceride. So the triglyceride has a glycerol backbone or crosslinker, the thing that's holding the 3 fatty acids onto it. Now they're no longer fatty acids. They're instead of stearic acid, it's stearate. Instead of oleic acids, it's oleate. It's the ester. It's the ester linkage to the glycerol, and that's your triglyceride. So if you looked at it here, here's your glycerol, here's your 3 fatty acids. You strip out this water, you form an ester, and your 3 fatty acids coming off of there. All right, so the triglyceride has only 2 components, glycerol and fatty acid. Just happens to have 3 of them. Now, mixed triglycerides. Mixed, what does that mean? These 3 fatty acids typically are 3 different fatty acids that are on there. Rarely in nature will you see a triglyceride, I'm not sure if you ever see it, where there's a glycerol and 3 stearates on it. So when we say beef fat is high in stearic acid, that's not the only fatty acid on beef fat. There's other fatty acids there. So mixed, more than one, usually 3 different ones. So here is a good oversimplification of the triglyceride structure. You have a glycerol with 3 fatty acids attached to it. And later on you'll see a slide with phosphoglyceride looks a lot like this. It just differs right here. right, so all of that other part of it is the same as the triglyceride. All right, if they are solid, we refer to them as fats. So lard, we would say, is a fat. Olive oil, we say, we don't refer to it as olive fat. We refer to it as olive oil. It's a liquid. Coconut oil, corn oil. Coconut. Yeah. Why do we call it coconut oil? Maybe because of MCTs. That is coconut oil. MCTs are liquids. Yeah, why don't we call it coconut fat? I don't know. Maybe because it comes from a plant. Or it has a relatively low melting point. You know, it doesn't take much to make coconut oil an oil. You can hold it in your hand and it'll start turning to a liquid. Okay, here's an example here showing you this mixed triglyceride. Now here's beef fat. Now here's 3 different types of fatty acids. Saturated, 16 to 18 carbons long. So here would be your stearic acid component. Unsaturated, C16 to C18. Here's your oleic acid portion, and then something else, maybe a small chain, a short chain saturated fatty acid. So the triglycerides that you would extract from beef fat will have this composition. Olive oil, which we've been talking about, has a lot of oleic acid, a little bit of stearic, and a little bit of this. This is why this one is a liquid at room temperature, and this one is a solid at room temperature. And you could do this with anything, sunflower oil, corn oil. You can go right along here and you can look this stuff up. It'll tell you, here's the fatty acids in this oil. Here's the 3 fatty acids that are in there. And, well, here is a list, but I don't have the top of that thing. That didn't come in very well. But you could do that. Cocoa butter, cod liver oil, coconut oil, corn oil. You can look this stuff up pretty easily. What are the different fatty acids that make it up? Okay, now triglycerides can undergo reactions. This is why we call them saponifiable triglycerides. You can react them with sodium hydroxide. They can undergo hydrolysis. Just react them with water in the presence at low pH, and they will hydrolyze into the fatty acid and the glycerol. And then you can hydrogenate some of them. Oleic acid. You could hydrogenate it and convert it into stearic acid. But that's exactly how we form trans fats, by trying to hydrogenate this. Partially hydrogenate. So if you want to stay away from trans fats, if you look at a label and it says partially hydrogenated vegetable oils, that's usually my key to put it back on the shelf. All right? I don't eat stuff with those ingredients, because what they have done is they've tried to change the melting point of it. That's what they were doing with margarine. Margarine, they took corn oil, partially hydrogenated it so that it would turn into a solid. It's not an oil any longer, it's a solid. And they would get it just right at the melting point they want. So you take your toast out of the toaster, you put that margarine on there, and it starts melting, and everybody loved it. But it was doctored up corn oil. So let's look at these 3 reactions. All right, so what is this? Hydrolysis. So here's our triglyceride. Here's our 3 ester linkages reacted with 3 molecules of water in the presence of an acid, and there's lipase. Now that's chapter 19 tomorrow. we'll be talking about molecules with an ASE ending. That's an enzyme. So here's an enzyme in the body that will break down a triglyceride into glycerol and the 3 fatty acids. Let me just move this over just a little bit. See that here's your carboxylic acid ends. You got your fatty acids. And that's the first reaction of triglycerides, hydrolysis. Second one, saponification. Same deal. Triglyceride plus 3 sodium hydroxides gets glycerol, and your 3 fatty acids now are the sodium salt. So instead of palmitic acid, you have sodium palmitate, sodium oleate, sodium linolate, or linoleate. That's saponification. And these are your soap molecules. So if you took this oil and wanted to make soap out of it, this is the reaction you would undergo, and those would be your soap molecules. Why? Because they're got a hydrophilic end right here, likes water, hydrophobic tail, and you have the makings now of a surfactant, a molecule that's active at this interface between water and oil. The oil-water interface, a surface active agent, which is soap. Hydrogenation. Okay, I just told you when you might want to do that. You don't like the melting point of this triglyceride, you hydrogenate it, and what they're doing right here is they're partially hydrogenating it. And let me show you. See that 2 right there? There are 2 of these groups here. There's a double bond. So there's one carbon-carbon double bond there, and there are 2 carbon-carbon double bonds there. Three of them. 3 double bonds. They're reacting it with 2 moles of hydrogen gas. And what are those going to do? Those are going to hydrogenate these 2 double bonds. So now we don't have them anymore. We have taken that unsaturation and saturated it. But there's a 3rd double bond right there. We didn't have enough hydrogen to do that one. That's the way they would want to do it, because that gives them a certain molecular weight. But when this molecule comes through this process, this is no longer cis. It's a mixture of cis and trans. And that's why partially hydrogenated vegetable oils are going to have some trans fats in them. It isomerizes. This catalyst right here will add this hydrogen to these 2 double bonds, but it will flip that cis, some of them to trans, some of them back to cis again, but then you'd have a mixture of cis and trans. That's hydrogenation. All right, the first reaction, hydrolysis, is a natural reaction in the body to break a triglyceride down into glycerol and fatty acids. Saponification is something we do outside the body to make soap. Hydrogenation is something we do outside the body, unnatural processes to make to change the boiling point or the melting point. All right, hydrogenation can result in trans fats. All right. So I said there's one slide on waxes. Beeswax. What is beeswax? It's not a triglyceride, but it does have an ester linkage. It has a fatty acid, like palmitic acid, and a very long chain. You see there's 29 carbons there. A very long chain alcohol, not glycerol. Glycerol's only 3 carbons long. This is 30 carbons long. Non-polar. 17 carbons going on here. Non-polar. This stuff is very non-polar. You can leave beeswax out in the rain for months. It's not going to hydrolyze. It's impervious to water. It is non-polar. It's hydrophobic. Keeps the bees pretty nice and dry. Some other parts like earwax is a wax. It's made of this kind of stuff. So that's waxes. They are saponifiable. If you mix this up with sodium hydroxide and could somehow get the sodium hydroxide near this bond, you could break that up. But don't worry about it. Just understand what waxes are. Okay. You all right? Everybody with me? We're through the first main category, triglycerides. So we've gone through this. 2 components, glycerol, fatty acid. Okay, now we're going to shift on over into phosphoglycerides. Remember that simplified triglyceride? There's something, this slide has something overlaid on something else. So sorry about this. This is garbage. But here's what the thing to think about. So glycerol, 2 fatty acids, and then a phosphate group with something on it. All right? And remember the triglyceride was just 3 fatty acids. This is your triglyceride. This is your phospho. Okay. Okay, now we're starting to venture into the realm of the cell membrane. Phosphoglycerides is the most abundant molecule that makes up your cell membranes. Now you've got about, well, I don't know what you've got, 3 to 10 trillion cells in your body. Every single cell has this protective layer or cell membrane around it. What is that cell membrane made out of? In most cases, phosphoglycerides. There's other things in there. About 60% of it will be these kinds of molecules. So don't let anybody convince you that you can live without fat or you need no fat in your diet. There are very essential fats in your nutritional makeup and in your body. And phosphoglycerides is one example of it. All right, so here's an example. Here's your glycerol backbone. Here's a fatty acid, palmitic. Here's an unsaturated fatty acid, let's say oleic. And then you're going to have a phosphate group linked over here to this last 3rd carbon. And here's your phosphate of phosphorus with 4 oxygens around it. And then on one of those oxygens there is X, some component, like choline, a quaternary ammonium cation. We looked at this in chapter 15. Here is a nitrogen with 4 carbons around it. 1 and 3 methyls, 4 carbons. It's a quaternary ammonium ion. Another possibility for X is ethanolamine. So imagine X is this molecule, and you've got an amine. This H would be gone, this O would be that O. So imagine, boink, you pop this up into there, and that is your OX group right there. Serine, the amino acid serine, you put it on there, and you have another phosphoglyceride. So these amino acids are not just in proteins, they can pop up other places. All right, so they're using PG as the abbreviation for phosphoglyceride. PG is containing choline, phosphatidylcholine, also called lecithin. Phosphoglycerides containing ethanolamine, they're cephalins. These play an important role in blood clotting. And this is your serine. So here's your phosphate group. There's your serine amino acid on there. There's your two fatty acids. Okay, now you might be asking yourself the question, to what level of detail do I expect you to go here? Danielle's eyes look like saucers. That level of detail. You don't have to go beyond this. You should be able to draw a triglyceride. You should be able to then kind of, from the triglyceride, make a phosphoglyceride with this phosphate group there and just the letter X, indicating that there's some additional component here. You define X and you know what phosphoglyceride you're talking about. I don't expect you to know choline from ethanolamine or serine or any of that level of detail. I think your homework has you answer a question coming down to that level of detail right there. No? Yes? Maybe? Samantha doesn't know yet. Okay, so that's phosphoglycerides. Okay, now we won't go into a great deal of detail. I'll show you the structure here. I'll introduce you to the name sphingolipids. Sphingolipids. And they get that name from this unit here, the sphingosine. What's important here? Well, of those 3 trillion cells in your body, some of them are nerve cells. I don't know how many nerve cells we have. But the nerve cells use a special lipid, sphingolipids, as their membrane, for their membrane. And then all the other cells of the body are using phosphoglycerides. So phosphoglyceride is the generic cell membrane molecule in your body. Sphingolipids is a specialized cell membrane molecule for nerve cells. So that's the thing that distinguishes these. I do expect you to appreciate that nerve cells have a specialized cell membrane molecule, lipid, and that's sphingolipids. So, for example, sphingomyelin, or the myelin sheath. You've heard about the myelin sheath? That's wrapped around the neurons. All right? That's the cell membrane that's wrapping around the nerve cell, and even the things that are coming out from the nerve cell has a myelin sheath around it. And they're using sphingolipids to make that. All right, so instead of having glycerol, I want you to see sphingosine is not glycerol, but it is taking the place of glycerol in the sphingolipid. You got a CH2OH down here, CH2OH on glycerol. Up here where you'd have an OH, and the next carbon up where you'd have an OH group right here, you have an amine. And then the top carbon, where you would have an H, you have a long chain, a long carbon chain here. So So you don't have 3 fatty acids, but you do have a non-polar chain here. You're going to put a fatty acid. You're going to put a fatty acid right there. So there's your long non-polar chain. Here's a fatty acid, but it's bound there not by an ester, but by an amide. And then over here you can have a phosphate group and something over there, and it defines a particular sphingolipid. So there's one fatty acid, there's a nonpolar chain, and something here. These are more complex even than phosphoglycerides. Have an even more complex backbone, sphingosine. See if we have some more examples. Types of sphingolipids. So sphingomyelin. Sphingomyelin. You can see that. So here is your normal nonpolar chain right there. Here's your fatty acid. So you got these 2 nonpolar tails on sphingolipids. And then bunched up in here is a lot of oxygens, phosphate, negative charges, positive charge, very polar. Very polar head, 2 nonpolar tails, and that's your sphingomyelin molecule, making up the myelin sheath. All right, I don't expect you to draw these, but to know that sphingolipids are the major component of nerve cells. All right, here's a few more. Here's one with that X group is a sugar. Here's a sugar where it's glucose. Here's one where it's galactose. All right? So your body is using these molecules for different things, just like you at home. You got a pantry. You go home and you say, oh, well, let's see, what can we make tonight? Well, let's see what we have. I'm going to put this together, and you come up with a different recipe every night because you have the raw materials for it. Your body has these raw materials, glucose, galactose, different things, and it's pulling them together and making the thousands of different molecules, active molecules it needs to do certain things in your body. Ganglioside. Now here's one where just instead of just one sugar, you got, that's the O antigen, the ceramide, the O antigen in the bloodstream. All right, so so ceramides, you just have that X group, going back to that third group right here. Right in here, you've got an X. You got an X right here. They're saying if X is hydrogen, it's a ceramide. If it is this phosphocholine, it's sphingomyelin. If it's glucose, it's a glycolipid. Here's a lactoceramide, ganglioside, etc. And then there are diseases, genetic diseases associated with these things. So it would be you'd lack, if an individual genetically lacks the enzyme to metabolize or make these different end groups. So here you can see one that affects the sphingomyelin. It is of great consequence. It will affect the brain. They're just different genetic diseases here: Tay-Sachs, Gaucher's, etc. So when an infant is born and they do this genetic testing on them, they're testing, I assume, a number of these things to see the ability to do these different things. All right, some of this stuff goes a lot more detail than we need to. Okay, steroid. All right, on your notebook, on your notes, here's something I want you to do. Got a sheet of paper, got a blank sheet of paper. Start it like here. We're going to make this big. What's this going to look like? And this is the last class, steroids. The last class of lipids. Steroids. All right, so start out by drawing a nice six-membered ring right there. All right, so I can do it right here. No, I need to go down a little bit. Like about right here, a nice six-membered ring. All right, now on that six-membered ring, draw another six-membered ring. Okay, now follow me here. You got two six-membered rings right next to each other. Now here, draw a six-membered ring, but it needs to come off of this upper right-hand corner of the second ring. And finally, come right across here and put a little house on it. Five-membered ring. And what you have right there are four fused rings. Fused. These two carbons right here are in both of these rings. These carbons are holding, there's not two six-membered rings, it's kind of butting up next to each other. They're fused to one another. Fused here, fused there. And this is the steroid nucleus. All right, so if I say draw the steroid nucleus, that's what I expect to see. And it looks like this. Here's the steroid nucleus here. Here it is drawn pretty much the way I've gotten it drawn there. You see there's four carbons there, and there's two more right here, and then four more here, and four more here, and three more over there that make up that ring. So there's a total of about 17 carbons. That's the steroid nucleus. Isoprene is shown over here as the precursor. Isoprene is the monomer, the individual molecule that the body uses to manufacture these steroids, synthesize. We don't usually say manufacture. Usually going outside the body, but synthesize the steroid nucleus. All right, the key steroid is cholesterol. All right, so here's your four fused rings. You got a methyl group here, an OH over there, another methyl here, and this carbon tail up here, that's cholesterol. Here it is more simplified. There's a double bond here. Right there, I haven't made these aromatic. They usually are not aromatic, although there are some steroids with aromatic rings. So cholesterol ends up being the precursor for the synthesis of most other steroids in the body. So you're making the other steroids from cholesterol. All right, so here's a kind of a flow diagram. Cholesterol, the body would then, through an enzyme, every one of these lines right here would have a different enzyme, a different protein molecule that carries the cholesterol through a chemical reaction to turn it into pregnenolone. I don't know how to pronounce that. Pregnenolone? Pregnenolone?
Progesterone.
No, this one up here.
The next one.
Pregnenolone. All right? And then pregnenolone, progesterone. You can see that progesterone is the precursor for testosterone. That is the precursor for estradiol. So the female sex hormones are on either side of the male sex hormone, testosterone. So even in the female metabolism, you have to go through progesterone, testosterone to estradiol. Cortisol, aldosterone, this is a steroid that is critical to the reabsorption of minerals in the kidneys. It's controlling whether certain ions will be released through the kidneys into the bladder or whether they will be retained. Aldosterone has a lot of role to play in that. These are all steroids. So there's some modification of this. Let's take a look at some of the differences. They're not huge differences. So there's estradiol, diol, you see the diol. And this ring here is aromatic. So there are 3 double bonds in that ring. So that's aromatic. Testosterone, it's got an OH, it has a ketone here instead of an alcohol, and it's not aromatic. Not too different, but some subtle differences there. Okay, here's one. This is vitamin D3. It doesn't look like it has that nucleus, but there's one ring, there's another ring, and if you were to break this bond right there, that would unravel it into that molecule right there. So imagine that bond gone, and this would be vitamin D3. So it basically had the steroid nucleus, but we've eliminated one bond right there, and it's unraveled. So that's also a steroid. It is lipid, it's water insoluble. It's a fat-soluble vitamin. I take a little bit of D3 every morning, and it's liquid. I just drop 3 drops on top of a glass of water with a spoon. I just take it, and that's 3,000 international units of vitamin D3. Vitamin D3 is fairly chronic deficiency in the population. If you were to go have your vitamin D3 level checked, I don't know what you would find. It's probably just my age. But at my age, it's deficient. All right? It's usually very deficient in people that are never getting the sun or don't get a lot of contact with the sun. So, and doctors are saying it's an important vitamin to keep up their good levels. Okay, here's testosterone, progesterone. All right, both steroids. Steroid nucleus, methyl group, methyl group, methyl group, methyl group. Ketone, ketone, double bond, double bond. Big difference is right here. So, very similar molecules. Subtle differences in these molecules obviously have huge differences. Now, the thing about steroids, they can go through the cell membrane pretty easily and go down into the nucleus of the cell and interact with DNA without a whole lot of interference. So steroids, where the cell normally really controls what comes in and out of it, steroids go in and out of the cell pretty easily. They go through the cell membrane. pretty easily. Okay. All right, and then let me just go over a few of the critical points about cell membrane structure, and then we'll call it quits here. Okay, so prokaryotic cells, single-celled animals, living things, have a very simple cell membrane. Animals and human beings, eukaryotics, multicelled animals, have a more complex cell membrane. The normal antibiotic, what's an antibiotic? It's going after bacteria, is going after the bacteria's cell membrane. And they have been engineered to be detrimental to the cell membrane of bacteria and not detrimental to eukaryotic cells, or the cells of your body. This is why you can take an antibiotic and it doesn't kill your cells, it kills single-celled organisms. But it's also why it cleans your intestines out of the probiotics, kills all the bacteria in your intestines, because it's going after the cell membranes of those. So what does the cell membrane look like? It's a lipid bilayer. Lipid bilayer. Okay, here's one layer of lipid. Here is the second layer, juxtaposed to one another. This is hydrophilic out here. Hydrophilic. And in here is hydrophobic. So it's hydrophilic on one end, it's hydrophilic on the other side. Hydrophilic. So what do you have here? You have water up here, you have water up here. There's an aqueous environment outside the cell, there's an aqueous environment inside the cell. Cell's full of water. And the bloodstream's full of water. And so what do you have here? You got a barrier. You have a hydrophobic barrier that is going to keep things from going in and out of the cell unless specified by the cell. All right, so it gets a little more complicated than that. The blue with the tails is your lipid bilayer. This is a cell membrane. Now, embedded in the cell membrane are proteins, specialized proteins. There's something like that is a sodium-potassium channel. There's something like that is a calcium-magnesium channel. Allows calcium-magnesium ions in and out of it. Different things. Different ways in which certain things can pass in and out of the cell, that living cell. Very complicated. There's stuff on the surface. This would be where you'd have stuff that would decide whether this is foreign or natural to the body. It's detecting whether this is something unusual and to be guarded against. So there's your cell membrane. Cholesterol is embedded in here. Here is where I believe, when you get into cell membrane theory, that these kinks, the fact that these cis bonds can make a kink, play a role in here. They're making certain shapes and places where certain things can be embedded in the cell membrane. Because that's what you would have. This would be on glycerol. This would be one of these heads, and this tail is what's flowing down into this lipid bilayer. And then you got another tail coming up, and you have your hydrophobic region. Now the steroids can go through that because they are lipid. They're fat soluble. This is why they can get through here. easily. They're fat soluble. So the membrane is 60% lipid, 40% proteins. Yeah, and I think we've covered these already.